So, good evening, everyone. Let us start today's discussion. Let us continue from where we have left. So, today, this will be the fifth lecture, right? The class for the fifth lecture. So, this will be mainly concentrated on slabs, okay? Design of slabs we will be focusing on. So, up till last class, we were basically, we basically concentrated on beams. Okay, so first we had learned the singly reinforced beam, then doubly reinforced beam, right? Then we had gone for T beams, flange beams, and I think last class we studied the shear, design of shear, right? So now we will apply all these concepts, okay? Like what we have learned for beams, we will apply all these concepts in case of slabs, okay? So the larger picture will almost be the same, but the mechanism of how to, evaluate or how to design the slabs, it will be little bit different, okay? So let us see how it is, in what respect it is different and in what respect it is similar, okay? So let us start, okay? So before we go for design of slab, we have to understand few terms, okay? Terminologies we have to understand and we have to define also, so that it is easier for us when we, it's just to easier for us to understand when we directly go for the design part, okay? So the most important term we have to like one of the most important term we have to understand is the effective span, okay? So what is an effective span, okay? So for that we will be referring the IS 456 2000 code. Okay. So as per this code, if you see, as per clause this one 22.2. Okay. So as per this, for simply supported beam or slab, okay, the effective span of a member that is not built integrally with its supports, okay, shall be taken the lesser of the following two: clear span plus effective depth plus depth of slab or beam, or center to center of supports. Both basically mean the both basically are the this one definitions for clear span. First we go for center to center. If it is not possible, then we go for clear span plus effective depth. Okay, so that is mainly for a member, okay, which is not built integrally. That is not basically it is not continuous. Okay, so it is not, and the concrete is not flowing directly from beam to slab to supports or everything. So it is not cast monolithically, okay? It is separate, you can segregate, okay? So for that purpose, the basically the effective span is the center to center distance between support, or clear span plus effective depth of slab or beam, right? So if you see this diagram, this is the clear span, okay? So this is basically end to end distance, okay? Near end to near end distance. So that is the clear span, plus when you add the half of width, okay? Half of width plus half of width, that is actually basically the width, okay? So that becomes the center to center distance, right? And if you don't know what is this, we just go for the depth, okay? So we add the, if this one effective depth of slab or beam. For this case, if we don't know the width, then like this we find the effective span, right? So based on this effective span L, okay, so we will get the moment and shear like this, okay? So if it is a uniformly distributed load W, then the moment will be W L square by 8, okay? And if W into L is equal to total load capital W, if we take, it will be capital W L by 8, okay? And similarly shear will be W L by small W L by 2 or capital W by 2, as you have must learned in mechanics, right? So this small w basically refers the uniformly distributed load, and capital W basically refers a point load or total load. Okay, so that is basically the case for a single beam. Okay, which is which is different, which is not built integrally. Okay, so it is separate beam or slab. Okay, now, in the case of continuous beam or slab, okay, if the width of the support is less than 1 by 12 of the clear span, then the effective span shall be as per simply supported case. Okay, if the width of the support is less than 1 by 12 of the clear span, the effective span shall be as per simply supported case. Okay, so this will be for n span with 1 n. So that is basically general condition. Okay, now for this one, this this will be valid, I think, for this one, for n span with 1 n fixed and the other continuous, and second for the intermediate span. So basically two types of this will be there in continuous beam. Okay, one will be continuous beam or slab. Two cases will be there. One will be end space once end span with one end fixed and the other continuous generally, and the other will be intermediate spans. Okay, so in both the cases the effective span shall be the clear span between the supports. Okay, so in this case it is the clear span. Okay, it is not the plus how width or something, plus width or depth, it is not required, only the clear span between supports. Okay, similarly, for end span width, so that is the general case. Okay, when it is one, because generally the end span is generally fixed. Okay, but that may not always be the case. Say for example, for end span with one end free and the other continuous, if it is not fixed but free, okay, then the effective span shall be the lesser of the following two, that is clear span plus half the effective depth. Okay, or clear span plus half the width of the discontinuous support. Okay, so out of these two the minimum we have to take. Okay, for end span free end and other continuous, for that case the effective span will be the lesser of these two values. Okay, so in the case of, similarly in the case of spans with roller or rocker bearings, this first case was for this one, the fixed end and continuous. Second was for free and continuous. Now in case of spans with roller or rocker bearings, so here basically the rotation will be allowed. Okay, translation will not be allowed, but rotation will be allowed. The effective span shall always be the distance between the centers of bearings. Okay, so here like it is almost similar to this one, simply supported. So it will, here the effective span shall always be the distance between the centers of bearings. Okay, now if the case is cantilever, okay, so in this case the effective length of a cantilever shall be taken as its length to the face of the support, okay, plus half the effective depth. Okay, so the effective length of a cantilever shall be taken as the length to the face of the support plus half the effective depth. Okay, because the other end is free, that's why. Or two, the length to the center of support where it forms the end of a continuous beam. Okay, so this case can also be applied, the length to the center of support, okay, where it forms the end of a continuous beam. Okay, so basically the this one, the last portion, the end span, like basically the no, exterior span, that's why it will form the end of a continuous beam, right? So these are some of the this one definitions of clear effective span for various cases. Please go through and understand for each of the cases how it will behave. Okay, so yeah, so that is for the beams and this one, continuous beams and slabs. For frames, in the analysis of a continuous frame, center to center distance shall be used. Okay, so for a frame, portal frame or something, so in the analysis of a continuous frame, so a portal frame is basically one, I think. So having, you know, 2 3 frames continuous, so their center to center distance shall be used. Okay, so yeah, so this is a portal, this one continuous frame, right? So here we have to consider center to center distance. Okay, so these are the basically the definitions of effective span. Okay, now let us go through moment and shear coefficients for continuous beams. Okay, so this will be as per clause 22.5 IS 456 2000. Okay, so substantially uniformly distributed loads over 3 or more spans which do not differ by more than 15% of the longest. So you know, this is mainly valid for uniformly distributed loads. Okay, so these loads should be uniformly distributed and it should be over 3 or more spans. Okay, so firstly it should be UDL, and secondly at least 3. Okay, 3 spans, and the UDL should be either equal or the variation should not be more than 15% from the maximum value. Okay, so out of this it should not it should be within this limit for, you know, going finding the moment and shear coefficients for continuous beams. Okay, so these are the as a this one requirements. Okay, so so for if the variation is not more than 15% and spans are more than 3, so we can use these tables. Okay, this full table is given in this one, page 36 of IS 456 table 12. So we will be going through part by part. So for dead load and imposed load, which is for dead load and imposed load, that is fixed. Okay, so there the span moment will be 1 by 12. Okay, near middle of end span. Okay, and the at middle of interior span it will be 1 by 16. Okay, so it will be more at the end span, okay, middle, and this is plus because this is sagging moment. Okay, whereas in the support moment case this will be in minus because it is hogging moment. Okay, and so it will be minus 1 by 10 at support next to the end support. Okay, and at other interior supports it will be minus 1 by 12. Okay, so at the end support it can be 0. Okay, if it is, you know, if there is no restraining, okay, moment is not restrained, so it will be 0, like simply supported. But if it is fixed, there will be some value. So yeah, so that will be dependent on that case. But for the interior ones, okay, like next to the end support it will be minus 1 by 10, and other interior supports it will be minus 1 by 12. So minus is because it is hogging. Okay, so that is, it is restraining the moment, and this is the actual moment that will be this one, that will be uh, and that will be you know, that will be generated because of the movement of loads. Okay, so this will be 1 by 12, that is sagging moment, and this will be 1 by 10. So this is the coefficients basically, right? And that is for bending moment coefficient for dead load and imposed load fixed condition. Whereas in the shear force whereas in the case of this one, similar for the similar criteria, dead load, imposed load, fixed condition, the shear coefficients will be like this. Okay, so at end support it will be 0.4, at all other interior supports it will be 0.5, and at support next, just next to the end support, the outer side will be 0.6 and the inner side will be 0.55. Okay, so this will be the four cases. Like end supports it will be 0.4, the support next to the end support, the outer side will be 0.6, inner side will be 0.55, and all the other interior supports it will be 0.5. Okay, so yeah, so if you say this, take this as the case. Okay, so as we just discussed in the tables, so m value here middle it will be 1 by 12 wl. Okay, so w is the total load, and effective length, effective span is l. So basically you just need to so if you can see here 1 by 12, so this is the value, right, near middle of end span. So basically if you see, we just need to multiply the load and the span with the coefficient for getting the moment. Okay, for predicting the moment, and for the shear force we just need to multiply the load with the coefficient. Okay, so no need of L. Okay, so simply just multiply the load with the coefficient and load into span with the coefficient for shear force and moment respectively. Okay, so here also it is zero point 0.6 as we just discussed here, outer side 0.6. Okay, next to the end support, right? Okay, so again these conditions were basically dead load and imposed load fixed. Okay, but if there is no dead load, only imposed load, and that is not fixed, okay, so that is moving, then it will be little different. Then what happens for bending moment coefficient case, the span moments near middle of end span it will be 1 by 10, and at middle of interior span it will be 1 by 12. Okay, and at support next to the end support it will be minus 1 by 9, and at other interior supports again it will be minus 1 by 9. So in both cases, okay, it will be minus 1 by 9. Okay, so clause 22.5.1 as per IS 456 2000. So for moments at supports, okay, for moments at supports where two unequal spans meet, okay, or in case where the spans are not equally loaded, okay, the average of the two values for the negative moment at the support may be taken for design. Okay, so at those supports, you know, where in either directions the spans are unequal, okay, or in cases where the spans are not equally loaded, then the you know, then the negative moment at the support, that is a hogging moment at the support, okay, that will be different. Okay, so we will take the average of the two values. Okay, so we will take the average of the two values for the design purpose. Okay, so that is 22.5.1. Similarly, as per clause 22.5.2, that is beams or slabs over free end supports. Okay, so it is a free end. Okay, so yeah, so beams or slabs over free end supports. So in that case where a member is built into a meson, so basically this free end support is basically a masonry wall. Okay, so because as compared to a RCC structure, the masonry wall is no it does not have any capacity to resist the force or moment, right? It can resist the translation as well as rotation. Okay, so we need like it is not a structural member basically, right? Masonry wall is not a structural member, it does not have capacity to resist, right? So that's why we can say this to be an example of free end support. Okay, So where a member is built into a masonry wall which develops only partial restraint. Okay. So something will be definitely be there, but that will be very partial. Okay. That will not be absolute. Okay. So that's why movement will be there, both translation and rotation. So when a member is built into a masonry wall which develops only partial restraint, the member shall be designed to resist the negative moment at the face of the support of WL by 24, where W is the total design load and L is the effective span. Okay. So this one, the member shall be designed in such case to resist the negative moment at the face of the support of WL by 24. So this value we directly take, okay. This value we directly take over free end supports, okay, like masonry wall. So we have to member shall be designed to resist the negative moment of WL by 24, okay, for that cases. So 1 by 24 is the moment coefficient for that case, okay, or such other restraining moment as may be shown to be applicable. So if there are some, if we are able to, somehow know, okay, so what will be the restraining moment, okay, uh, which will be needed or which may be applicable, we can apply that also. If we don't know, we will take the coefficient of 1 by 24 and multiply by W into L, okay. So that is the case for beams or slabs over free and supports like masonry wall, okay. So again, as per clause 22.5.2, beams or slabs over free end supports. Okay. So this is a yeah, similar. So continuing. Okay. So where a member is built into a masonry wall which develops only partial restraint, the shear coefficients at the end support given in table 13, okay, may be increased by 0.05. So yeah. So this was table 13. So basically, this one, shear coefficient at the end support may be increased by 0.05. So basically, for a free and support case, that is for a masonry wall case where a member is built into a masonry wall, the moment coefficient at the face of the support will be 1 by 24, okay, and the shear coefficient, okay, shear coefficient will be basically this one, your this one, 0.4, okay, plus 0.05, okay. So as you can see, so this is 0.4 plus 0.05. So where a member is built into a masonry wall which develops only partial restraint, the shear coefficient at the end support may be increased by 0.05. Okay. So we just have to add plus 0.4 with plus 0.05, okay, for the masonry wall condition, that is free end, okay. So those are basically the shear force coefficient and bending moment coefficients, okay. So how to predict, okay. So now, yeah, so now let us go into slabs in, in more depth, okay. So basically, if you see the reinforced concrete solid slab, okay, so basically there are four types, okay. There are four types. So these two are the most common, like these two are the most common, and these two will be these two we will be using in our design and in our course mainly. But there are four like four cases of slabs, okay. So there is one way slab, there is two way slab, there is flat slab, and there is flat plates, okay. So one way slab, okay. So one way slabs are those slabs, RCC slabs, where the Ly by Lx value is always greater than 2, okay. Say for example, if the slab is having a dimension of say 11 by 5 meter, okay. So we will always take the longer side as Ly, okay. So 11 meter will be Ly, and say for example the shorter side will be 5 meter. So Lx will be 5 meter, okay. So if you see 11 by 5, okay, so that will be definitely it will be greater than 2, right? It will be around 2.2 maybe, yeah. So it will be greater than 2. So that type of slab is one way slab, okay. But if the value or ratio of Ly by Lx is less than equal to 2, okay. Say for example the slab is having a dimension of 10 by 5 meter, okay, or 6 by 5 meter. So Ly will be 10 or 6, whereas Lx will be 5, okay. So 10 by 5 is 2, so again so it is equal to 2, so it is two way slab. Again 6 by 5 is also it will be how much, 1.2, so that is also less than 2, so it will be again two way slab, okay. Now if you consider the flat slab condition, so in flat slabs, okay, so what is a flat slab? So basically flat, flat term is there when the beam is not there, okay. So in one-way slab or two-way slab, okay, so beams are also always present, whether it is whether it is monolithically cast, or if, whether it is differently, okay, if it is present different in a different way. So in a isolated way, both slab and beam. So in both the cases, the beam is present in one way or two way slabs. Okay. However, in case of flat slabs, okay, in case of flat slabs or flat plates, okay, the term flat is used when there is no beam. Okay. So it is completely flat, okay, because beam will have some more height, right, more depth, right. So it will be something, more extension will be there in the corners, right, in the case of beams, as you can see in our houses. So definitely some extension will be there, okay. So that is the beam. But in case of flat, okay, whether slabs or plates, there will be no extension. So that's why it is flat, right. So it is flat, okay. So both in flat slabs and flat plates, therefore there is no beam present, right. Now the flat slabs are those have, which have this one, this drop panels, okay, or the this one column capitals, okay. So this is a column capital and this is a drop panel. So there is some support, okay, some support for the sharing of the load, for the distribution of the load from the slab to the column, okay. So there is some some more extension of this one is there, more extension of the column is there in uh, order to transfer the load properly from the slab to column, okay. So that there is no more no issue of any failure occurring. Most common failure is the punching shear failure, okay. So that failure will to avoid that failure, they provide some type of column capital, which is this, some extension, okay, of the column, or the drop panel, okay, which is a further extension. So when those are present, this is called the flat slab, okay. But when those are not present, it is simply a flat plate, okay. So this is a problem of punching shear failure of the columns, okay, and the slabs, mainly the slabs, okay. So it will just go down, okay. So that is mainly the shear locking failure, okay. So shear locking, there will be some extra shear, okay. So that will result in the failure, okay. So that shear locking problem will be there. So yeah, so that those topics are beyond our scope of discourse. So just understand that when there is no beam, it is called flat, and plates are those which does not have, which only have column and slab, whereas flat slabs are those which have support, column capital or drop panel support to the columns for the transfer of loads from the slabs to the columns, okay. So those are the cases. So as I just discussed, this is an example of two-way slab. So we will be mostly concentrating on two-way and one-way slab. We don't have to consider. We will not be studying panel and flat slab, because firstly it is not used in general way, and secondly that is beyond the scope of this course, okay. So if you see this, this is the one-way slab, okay. Here Ly by Lx will be greater than, definitely greater than 2, okay. And here this is the case of this is one way slab, sorry, and this is basically the two way slab, okay. So here the Ly by Lx value will be less than equal to 2, okay, as can be represented. The figures are basically self-explanatory, okay. So I just mentioned those. So this is basically a two way slab, this is a one way slab, seeing the size, okay. Now yeah, this is one way slab, this is two way slab, right. So now, yeah, so if you can see here, so if you take these cases, so this is a case of flat slab, so this is a drop panel, okay. So drop panel, and the other is the column capital. So I think this is a column capital, yeah, this is a column capital, and if there it is rectangle, it will be drop panel, okay. So this is a flat slab and it has nothing, so it is a flat plate, okay. So now let us basically study the various types of loading, okay, various types of loading that will be applied on the slabs in buildings, okay. So the various types of loadings, basically we will refer to IS 875 code, okay. So that is the code for various types of loads, be it dead load, live load, wind load, okay, and various other loads, and various other extreme various other hazard type of loads or extreme situation loads, say cold weather, ice load, something like that. And also combination, I think like there are 5 parts. First part is dead load, second is live load, third is wind load, fourth is I forgot, please check it. So it will be some special load, and fifth is a combination, okay. just leaving the earthquake load. Okay, earthquake load we have a separate code which is IS 1893. I think most of you have most of you know maybe. So so that is a separate code because of such a significant event in our country, the earthquake. Okay, so they have separated that earthquake code from the 875. Okay, that is basically 1893. Okay, but for other types of load we basically refer the 875. Okay, so from that you will see the self weight. Okay, that is the dead load basically is the 25. That is the basically weight of RCC, right? The RCC. So for a plain concrete PCC it will be 24. For RCC it will be 25. Okay, so 25 kilonewton per meter cube. So if you add finishes and partitions, okay, so that will extra, that will be adding 1.5 kilonewton per meter square. Okay, so apart from that, if you consider characteristic imposed loads, okay, so in the case of roof, okay, in the case of roof which is having excess, so there we have to consider more, that is 1.5 kilonewton per square meter. Whereas in the case of roof without excess, okay, so there the characteristic imposed load will be 0.75 kilonewton per square meter. Okay, so that is the case of roof. Okay, similarly in the case of floor, okay, so in the case of floor, in the case of residential building, so it will be 2 kilonewton per meter square. Okay, and in case of office floors, it will be 3 kilonewton per meter square. So basically office and this professional, like mainly the these commercial areas, so there will definitely movement of people will be more, so therefore the floor has to be designed for a more this one more load, more UDL. Okay, so that will be taken as 3 kilonewton per meter square, whereas for residential complexes, so it will be 2. Okay, 2 kilonewton per meter square. So these are the values taken from IS 875. These are taken from the part the second part, that is the live load, and this is mainly from the dead load, that is these two are I think from the first part. Yeah, first part. Okay, so these are the loadings we have to consider for the slabs in buildings. Okay, so for that we have to refer IS 875. Say now that is one important part. And after that we have to consider the concrete cover. Okay, so we have to find the clauses, the design guidelines for like design guidelines which we have to adhere for the concrete cover cases. Okay, how much we have to apply concrete cover, we have to follow this table. Okay, this clause and this code. Okay, so that is mentioned in table 16, clause 26.4.2, IS 456 2000. Okay. So in the case of mile exposure, okay, a nominal concrete cover should not be less than 20 millimeters. Okay. So that should be the this one minimum for mile exposure. However, if the main reinforcement is up to 12 millimeter diameter bar, in the case of mile exposure, the nominal cover may be reduced by 5 millimeter. Okay. So it can be 15 mm if the exposure is mild and the reinforcement is less than equal to 12 mm diameter. Okay, so then we can reduce the nominal cover by 5 mm. Okay, so 20 can become 15. Okay, so that is the case of concrete cover. Okay, apart from that, what a control deflection control. So in slab, one of the main criteria to check is the deflection. Okay, because that is a very important parameter. Okay, so this one, so it is one of the important parameter for slab is deflection. So we have to see whether deflection is within the acceptable limits. Okay, so for that we have to refer clause 23.2 IS 456 2000. Okay, so the final deflection due to all loads including the effects of temperature, creep and shrinkage, and measured from the S-cast level of the supports of floors, roofs and all other horizontal members should not normally exceed span by 250. Okay, so the final deflection due to all loads, okay, including the temperature effect, creep effect, okay, shrinkage effect. Okay, so creep we have just we studied I think in the first class itself. So that is the that is a long term deflection. Okay, after the instantaneous deflection. Okay, which decreases with time. So that is the creep. Okay, and shrinkage is basically the reduction in volume when the pore water inside the concrete evaporates. Okay, so including all these effects and measured from the S-cast level of the supports. Okay, so first like in situ when it was cast, from there when it is measured of floors, okay, roofs and all other horizontal members, so it should not normally exceed span by 250. Okay, so that is the value it should be always within. Okay, so that should be always maintained. Okay, And the deflection including the effects of temperature creep and shrinkage occurring after erection of partitions and the application of finishes, okay, should not normally exceed span by 350 or 20 mm, whichever is less. So this is basically including temperature creep and shrinkage. Okay, so only including temperature creep and shrinkage, the deflection should not be more than span by 250. And after that, if we have partitions inside the building as well as you know we have applied finishes, okay, so that will also create some load, right? So after including all those loads, then also the value should not be more than span by it should not normally exceed span by 350, okay, or 20 mm, whichever is less, okay. So basically this value is less than this value, sorry, this value is higher than this value, okay, this value is even less because denominator is high, right? Denominator is high, so basically we should always go for this condition, span by 350 or 20 mm, whichever is less, it should not extend it, okay. We can leave this condition because it will be more, okay. So if it is satisfying this, it will definitely satisfy this, okay. Okay, then your direction of this one, yeah, so yeah, so these are the two conditions for deflection. So basically we'll be considering span by 350 or 20 mm, whichever is less, okay. So yeah, apart from that, the vertical deflection limits, okay, may generally be assumed to be satisfied provided that the span to depth ratios are not greater than the values obtained as below. So basically these are the values, okay, below which it should be maintained, okay. So it is because it is not possible to it is not possible to it is not possible to measure after constructing, okay, or there is no use, okay, after you have constructed, okay. So basically we always consider try to make the span by span by effective depth ratio less than equal to this value when the span is up to 10 meter, that is less than equal to 10 meter. So if the ratio is less than 10 when span is up to 10 meter, we can consider that these conditions are satisfied, okay. So that is the meaning. So the vertical deflection limits may generally be assumed to be satisfied provided that the span to depth ratios are not greater than the values obtained as below. So for basic values of span to effective depth ratios for spans up to 10 meter, the cantilever will be for cantilever case the maximum value is 7, for simply supported it is 20, and for continuous it is 26, okay. So for spans up to 10 meter, the L by D, if you consider a span as L and effective depth as small d, so L by D value for cantilever it should be less than equal to 7, for simply supported it should be less than equal to 20, for continuous it should be less than equal to 26 when L is less than equal to 10 meter, okay. So for spans above 10 meter, we have to apply some modification factors, okay. So the basic values may be multiplied by 10 by span, okay, in meters, in except for cantilever, in which case deflection calculations should be made. So for spans above 10 meter, the basic values may be multiplied by 10 by span in meters, except for cantilever, in which case deflection calculation should be made, okay. So depending on the area and the stress of steel for tension reinforcement, the basic values shall be modified by multiplying with the modification factor obtained as per figure 4 IS 456 2000, okay. So basically as I told you, okay, uh, this your yeah, so basically these are the basic values, that is when L value is less than equal to 10 meter, okay. Apart from that, when 10 if L is greater than 10, this value has the value we obtained here, L by D value, so that has to be again multiplied by 10 by span, okay. And then found see, then we have to see whether it is less than this value, okay. And when the when there is reinforcement, okay, so then we have to apply the modification factor. For tension reinforcement there will be separate modification factor, for compression reinforcement also there will be separate modification factor, okay. So depending on the area and the stress of steel for tension reinforcement, the basic value shall be modified by multiplying with the modification factor obtained as per figure 4 IS 456 2000. So this is the this one, this is the chart, okay, as per figure 4 IS 456 2000. So this is the percentage tension reinforcement, this is the modification factor. But for this we have to first calculate the value of Fs, which is your this one steel stress of service loads. Okay, so for finding this, it's very easy. We have to just multiply 0.58 with the elastic yield strength of steel. Will it be whether it is to 415, 500, or 250, and then we have to multiply the value with area of cross section provided by area of cross section of steel. Sorry, area of cross section of steel required by area of cross section provided. Okay, so 0.58 into Fy into A as provided, sorry, A is required by A is provided. Okay, so the steel stress of service, that is Fs, is 0.58 into Fy into As required by Ast provided. Okay, so using that you can get the Fs value. Okay, so if it is this value, fine. If it is between this, we need to interpolate, right? So in interpolating and taking the percentage tension reinforcement, which is P basically. P is equal to Ast by Bd into 100, right? So taking the value of P, taking the value of Fs, we get the modification factor, which we have to multiply. Okay, so that is for tension. And similar for compression, depending on the area of compression reinforcement, the value of span to depth ratio will be further modified by multiplying with the modification factor obtained as per figure 5. Okay, so this is the figure 5. This is the modification factors for compression reinforcement. Okay, so this is percentage compression reinforcement. This is a modification factor. So yeah, so again this will be if that was pt, this will be pc. Okay, so it will be asc by bd into 100, right? So using that you will get this compression sorry, percentage, yeah, percentage compression reinforcement. And here luckily there is no fs value we have to calculate. We just take this line and find the pc value and compare and get the modification factor and just multiply. Okay, so after multiplying the basic values with modification factors, and if modification factors of tension and compression, and yeah, so and also this one the if the length is more than 10, then 10 by span, right? Sorry, span by 10, right? So all this multiplication, after that if the value is less than 20 for simply supported, okay, 7 for cantilever, and 26 for your this one continuous, then it is understood that the vertical deflection limit will be less than this one span by 350 or 20. Okay, so that is for tension compression. And even if we consider, say for example, this one, if the beams are flanged, okay, it is T beam or L beam, then the basic values be modified as per figure 6. Okay, and the reinforcement percentage for use in figure 4 and figure 5 should be based on area of section BFD, not BD, because B will then be the width of web. Okay, so we have to consider the flange width into depth. Okay, and there, yeah, so there you have to this one for flange beam, the basic values be modified as per figure 6, and reinforcement percentage for using figure 4 and figure 5 should be based on area of section BFD. So you have to then consider modification factors which are calculated based on BF. Okay, like AST by BFD, ASC by BFD into 100. So for figure 4 or figure 5, like that you have to multiply the modification factor, and also you have to multiply the reduction factor also. Okay, so as per figure 6, so that will be based that will be a function of web width divided by flange width. Okay, so definitely web width by flange width will be less than 1, right? So less is the value, more will, lesser will be the reduction factor. Okay, so like more will be the value of reduction factor. Okay, so it will be 0.5, 0.85, 0.8, 0.75, like this it will come down, and it will be constant at 0.8. Okay, zero point 0.8, it will not be less than 0.8, and maximum it will be 1 when the wave width is equal to flange width, that is it is not a flange section, right? So it will be lesser otherwise, so you have to multiply this also. Basically these three modification factors you have to multiply, and apart from that there is if the span is greater than 10 meter, it will be this one, we have to again multiply by span by 10. Okay, so these four are the factors you have to multiply, multiply with the this one L by D ratio. Okay, and after that if you get the value less than 20, less than equal to 20 for simply supported, less than equal to 7 for cantilever, and less than equal to 26 for continuous, so then the deflection limit is satisfied. Okay, so these are the cases we have to consider. Okay, so okay, so these are the some important parameters we have learned about before design of slabs. Okay, so these are important. So based on this, let us understand how to design a slab. Okay, so this is a problem, design of one way slab. Design a simply supported RCC slab for a roof of a hall. Okay, 3.5 meter by 8 meter inside dimensions with 250 millimeter walls all around. Okay, so this will be like a free end support. Okay, because it will be like, if we consider masonry, it will be free end type of support. So, and also this 3.58. Okay, so higher value is Ly, lower value is Lx. So 8 by 3.5. Okay, so it will be always, it will definitely be greater than 2. Okay, so that means it is a one mesh slab. Okay, so with 250 walls all around, assume a live load of 4 kilonewton per meter square and a finish 1 kilonewton per meter square. Use concrete M20 and steel Fe 415. Okay, so these are the cases we need to consider. Okay, and yeah, so for this calculation of, first we have to we need to calculate the factored loads. Okay, so before that we need to find the depth. Okay, effective depth as well as total depth. Okay, so let us assume that it is a the span by d ratio is 25. Okay, so 25, because maybe we are assuming this is a this one, although it is a simply support, actually it should be less than 20, right? So L by D value should be less than 20, but okay, we are assuming this as 25. So yeah, so assume span by D as 25. So effective depth D will be span by 25, which is equal to 3500 by 25, 140 Okay, and total depth will be D plus clear cover plus 5 by 2, right? Clear cover we have assumed as 15 because it is mild, and this one, the rebars are this one, yeah, rebars are less than 12, right? So less than equal to 12, so we can consider 15 Okay, but if it is not, we have to consider 20 Okay, so yeah, so clear cover is 15, 5 value is 10 rebar. So 140 plus 15 plus 10 by 2, which is comes to be 160 millimeter. Okay, so we have assumed 10 millimeter diameter. So the dead loads for the slab. Okay, so it is having a depth of, total depth of 160, right? So dead load for the slab will be 0.16 into 25, as we discussed the dead load on this one values. So it will be 4 kilonewton per meter square, sorry, 4 kilonewton per meter square, and the finishing load will be 1 kilonewton per meter square, right? So total it will be 5 kilonewton per meter square, and live load written as 4 kilonewton per meter square. So LL is 4 kilonewton per meter square. So factored load, that is the design load, therefore will be 1.5 into DL plus LL. Okay, so as we know, so 5 plus 4 is 9, and 9 into 1.5 is 13.5 kilonewton per meter square. Okay, so for, for the depth, basically we had to calculate the D value. Okay, for in order to find the dead load of slab. Okay, as per unit area. Okay, in terms of unit area. So effective span. Okay, so effective span based on the conditions. Okay, it will be 3.5 plus 0.25. Okay, half of both side wall width. Okay, so that will be one width of wall. Okay, so 3.5 plus 0.25 will be 3.75 meter, and otherwise the 3.5 plus effective depth, which is 0.14, right? 140 So 3.5 plus 0.14 is 3.64 meter, and we have to consider the lower value, right? Minimum value. So therefore effective span will be 3.65 meter, right? So therefore total load per meter width. Okay, total load per meter width will be 13.5 into 3.64, which is 49.14 kilonewton. Okay, per meter width. Okay, that is per meter. Okay, so that is the first condition, first step. Okay, calculation of factored loads. Second will be the ultimate moment and shear, evaluation. Okay, so finding the ultimate moment and shear. So mu value will be basically WL by 8. So that is the maximum. Okay, and if we all know from mechanics class that the maximum moment always occurs in simply supported beam. Okay, in the midspan, which is the WL square 8 value, right? So WL, if you consider it as a concentrated load, it will be WL by 8, right? So mu equal to WL by 8. So where W is this one, 49.14. Okay, 49.14. So everything is per meter width, although it is although it is a UDL basically, but we are considering it as a concentrated load. Okay, assuming that it is 1 meter width. Yeah, so in slab we always design for 1 meter width. Okay, as per 1 meter width we always design. Okay, so we can always consider that 1 meter width as constant. Okay, so that therefore it will be a concentrated load. Okay, so it will be 49.14 into 3.64. Okay, So 3.64 is a span divided by 8. Okay, so this will come out to be 22.3587 kilonewton meter. Okay, and view will be similarly, it will be WL by 2 or capital W by 2. So capital W is 49.14 divided by 2, which is 24.57 kilonewton. Okay, so, and this is this one, the cross section. 1000 is the width and 160 is the total depth. Okay, so VU will be W by 2, that is 49.14 by 2 or 24.57 kilonewton. Okay, so third condition, check depth for bending. Okay, so mu is equal to 0.138 fck bd square. Okay, d is square root mu by 0.138 fck b. Okay, so yeah, so that is the limiting condition, right? So limiting maximum moment carrying capacity for the concrete section, like the plane that the concrete capability. Okay, concrete moment carrying limiting moment carrying capacity for Fe415 bars, it is 0.138 fck bd square. So for I think for Fe500 it was 0.133 and fck bd square, and for Fe250 it was 0.149 fck bd square. Okay, so yeah, so d is equal to square root mu by 0.138 fck b. So mu is 22.3587 into 10 to the power 6, 0 divided by 0.138 into fck is 20, I feel. Yes, 20. And this one B is 1000. As I told you, we will always consider width as 1 meter. Okay, for slab. Okay, so that is always constant. Okay, so always consider 1 meter. So 1000 mm. So that then effective depth will become 90 millimeters. Okay, so yeah, so so that means our depth. Okay, so our minimum depth should be 90. Okay, but we have provided depth as how much? We have provided depth as 160. So 160, sorry, 140. So 140 is definitely higher than 90. So it is satisfied. Okay, minimum depth is satisfied. So then we have to check for shear. Okay, so shear tau v. Okay, tau v is equal to VU by VD. Okay, and VU is how much? 24.57, right? So into 10 cube by V is 1000 and B is 140. So tau V comes to be 0.1755 Newton per mm square. So from table 19 IS 456 2000. Okay, if we assume 100 AST by VD is less than equal to 0.15%. So we have just assumed this the minimum value. So tau C value is equal to 0.28. Okay, which itself is higher than tau v. Okay, so if tau c value is less than, even in fact if tau v value is less than tau c only, so basically shear reinforcement is not required. Okay, because it is uh, the 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 shear load. Okay, the design shear load is in fact less than the shear strength of concrete only. So stirrups is not basically required. Okay, so that means it is also satisfied in shear. Okay, and we provide nominal shear. Okay, which had the formula of if I remember this one, yeah, ASB by BSV, ASB area of steel in stirrups by B into SV should be greater than equal to 0.4 by 0.87 FY, if you remember last class. So that is the nominal shear value we give, but it is better to give, but it is not required because tau v is less than tau c. Okay, so now let us calculate the area of steel. Okay, so for that we will use this formula. Okay, so this comes from the derivation of this one, moment carrying capacity, and from equating the forces. Okay, tensile and this one compression and all. Okay, and finding the moment carrying capacity. Okay, so 0.36 FCK BXU into D minus 0.4 XU, right? So divided by D. Okay, so if we divide by D, and dividing by D, and equating, finding that term in terms of X by D, and in the limiting condition, so you get this formula. Okay, so sorry, this is a general formula. So if you put here limiting values, so you will get 0.13 fck bd square. Okay, so from using this formula we will calculate the area of steel. So yeah, so in this case mu is 22.3587 kilonewton meter, fck is 20 megapascal, b is 1000 mm, d is 140 mm, right? So plotting all the values, we get the x by d value 1.2 plus minus something. So as x by d value can be more than 1. Okay, so there, we don't take the plus value, we always take the minus. Okay, 1.2 minus something. So it comes to be 0.1685. So x by d is equal to 0.1685. So yeah, so basically the using that we will calculate the lever arm z, which is d into 1 minus 0.416 x by d, right? So here yeah, so here d is 140 and x by d is 0.1685 as we found just now. So 140 into 1 minus 0.416 into 0.1685, right? So that comes to be 130.186 millimeter, okay, the lever arm. And AST, okay, so we'll again use the this one moment carrying capacity equation for a true area of steel tension side. So AST equal to mu by 0.87 FYZ, okay. So mu value is 22.3587 kilonewton meter, divided by 0.87 into Fy value is 415 into Z value is 130.186, right? And so solving this we get the value of area of steel as 475.6 millimeter square. So this is the amount of steel we will require, okay. So the spacing, okay, spacing provided in the slabs, how much it will be? It will be we will consider 1000 mm, yeah, 1 meter width, as I told you, we will always consider 1 meter width divided by the number of bars required, okay. So spacing will be basically the width, which is 1000, divided by number of bars required. So number of bars required will be equal to area of steel required divided by the area of 1 bar, okay, which we have considered as 10 mm dia, okay. So that is how much? Pi by 4 into 10 square, 78.5 mm square. So number of bars required will be 475.6 divided by 78.5, right? So that will be the number of bars required. So spacing required will therefore be 1000 divided by 475.6 divided by 78.5, which becomes equal to 1000 into 78.5 by 475.6, which is 165.05 mm, right? So yeah, so checking the required conditions, okay, checking the required conditions, we can the conditions are like this, okay. It should be minimum of 3D 300 mm and the value we have found, okay. If yeah, that is the general case, and the lower we value, the lowest value we take as per 26.3.38 clause, okay. And if there is shrinkage in temperature, okay, we have to, it should also not be greater than 5D or 450 mm, okay. So all these factors we take into account, okay. So taking all these factors, we have found that we can take any value less than that value, okay. So lesser is better, okay. More or less will be the this distance, better will be the steel carrying capacity, but it should not be uneconomical. That is the thing, because cost will be also high because more steel is required, right? So that's why we take the minimum value as the maximum value, okay. So if now in this case, for example, it was how much? 300 mm. It should have been less than 165.05 mm. 3 into 140 is how much? 420 mm, right? And 300 mm, okay. So that means minimum of 165, 420 and 300, which is 165 itself, okay. So they have that, like that should be the maximum, it should be lesser. So they have provided 150, which is great, okay. So 10 5 and at the rate 150 mm center to center, okay. So by this condition, if you check the area of steel, okay, that will be required basically. So that will be how much? Yeah, that will be how much? So for that also you have to consider the number of bars required, which will be 1000, 1 meter divided by 150 mm, right? So 1000 by 150 into pi by 4 into 10 square, which comes to be 523 mm square. So we required 475.6, we provided 523, so better, no issue, okay. So minimum condition is satisfied. So yeah, so these are the clauses. As I told you, it should be always less than the obtained value 3D and 300 mm, okay, in general case. And against shrinkage and temperature, it should also not be greater than 5D or 450 mm. So like if it is satisfying this condition, it will definitely satisfy this condition, okay. So so we have to mainly consider this condition, 3D 300 and the obtained value, okay. So yeah, so that is a primary reinforcement, okay. And secondary reinforcement is always will be less than this, okay. So less than this means diameter will be less but spacing will be more, okay. So it will be 85 at the rate 250 mm center to center, okay. So here also these conditions are satisfied, 250 is less than 300 and 250 is less than 420, right? And 85, it will also the secondary distribution still is basically the secondary reinforcement, so that diameter will always be less than 10, less than this, okay, the primary one. So generally 8 is used, okay, or it can go for 10 if we change this to 12, okay. So yeah, so AST provided is 523 mm square. Percentage of steel is 523 divided by 1000 into 140 into 100, right? So it comes to be 0.373. Now we have to find the we are going for finding the deflection limit, okay? The deflection condition, deflection checking, okay? So for that, in the tensile modification, tensile steel, we have to apply modification factor, for which we need the steel service load (FS), which was 0.58 into Fy into AST required by AST provided. Okay, so we just discussed few slides back. So AST required was 475.6 mm square, if you see, and AST provided is this one 523 mm square. Okay, so Fs will be equal to 0.58 into 415 into 475.6 divided by 523. Okay, so that comes to be 218 Newton per mm square or megapascal. Okay, so yeah, so that is the this one, the chart, okay, figure 4 of IS 456, for which we required the Fs and PT value. Okay, so using both we can find the modification factor, okay, for tension reinforcement. Okay, so we have using the value of 218 and PT of 0.373%, we found the modification factor is 1.55, if you see. Okay, so L by D value will be, as it was simply supported, it will be 20 into 1.55. Okay, so therefore the limit should be like maximum limit should be L by D limit should be 31. Okay, so now you have understood. Okay, so now we have understood why it was taken as 25. Okay, so if you would have initially only you have assumed 25, it was like little bit confusing because maximum was 20 but we took 25. Why? But now you can understand, because after multiplying modification factor, it has gone above 25, right? If it still, if it still is less than 25, then we have to redesign. Okay, we have to take it, definitely take it less than the actual L by D. Okay, so this is the basic value. Okay, so we have to multiply this. Okay, so then only we have to compare whether our taken L by D is less than equal to the maximum value. Okay, so as 25 is less than 31, so the condition is satisfied. Okay, so our design is right. Okay, so therefore now we can calculate the D. Okay, so D is equal, like the D required. Okay, so therefore D required is equal to L by 31. Okay, where L is 364 meter divided by 31. Okay, so that was equal to 117.42 millimeter. So that was the D value which was required. Okay, 117.42 millimeter, but we have provided 140, so it will not be an issue. Okay, so yeah, so secondary steel, so this is the minimum value. We provided 140 mm effective depth and 160 mm total actual depth. Okay, so it is satisfied. Okay, so now if you see the secondary steel, okay, so yeah, so this the minimum as per IS 456 clause. Okay, so here it is this one, this, yeah, so as per IS 456, if you remember, in case of beam, okay, the minimum amount of area of steel required is this one, is as per the condition AST by BD equal to 0.85 by Fy, if you remember. Okay, so that is the minimum amount of steel required for beam, and the maximum required is 0.04 B into D, where B is width and D is actual depth, not the effective depth. Okay, that is for beam maximum reinforcement. Whereas in case of slabs, okay, so in case of slabs, the minimum requirement is either 0.15 BD, okay, B into capital D if mild steel is used, and if HYSD bars are used, we can go for 0.12 B into capital D. So as we are using Fe415, which is HYSD, high yield strength deform, so we can go for 0.12 BD. So that is the maximum steel. Okay, I mean, sorry, minimum steel required. Okay, so D is here the actual depth, not the effective depth. So from this you can see the amount of this one area of steel required is 0.12 B capital D percent. Okay, so actually is we have to divide by 100. So it is 0.12 into 1000 into 160 by 100, which comes to be 192 millimeter square. Okay, so if you see, these are the main steel bars. Okay, and these are the secondary bars. Okay, so like this you have to observe and you have to design. Okay, So for this one, so the secondary steel bars, we have to provide 8 dia bars. Okay, so we are providing 8 dia bars. So one bar 8 bar is having area 50 square. So spacing required will be 1000 divided by 192 by 50, which is 1000 into 50 by 192. It is 260 millimeters center to center, right? So like from this only, they have found the this one is 250. If you see here, date 250. So this is coming from here, okay, after design. So it should be less than 260, 420, and 300. So definitely 250 is better. Okay. So yeah, so if you see, this is the ultimate design. So these are the main reinforcement, okay, and these are the secondary reinforcement, okay. So if you see here one case, so this is 4 meter, okay. So this was actually 3.5 meter from here to here, okay. This is 3.5 meter, and this was I think 8 meter, right? So one thing, if you have observed here, which is different from beam, it is the placing of the primary reinforcement, okay. So in case of this one, in case of our, yeah, in case of beam, there is no concept of secondary reinforcement. There is always primary reinforcement only, either it is in tension or compression, okay. So there, if you see the reinforcements, primary reinforcements, or only the reinforcements are always parallel to the axis, okay. It is on in the direction of the axis. But here the primary reinforcement is perpendicular to the axis, okay. It is perpendicular, okay. And the secondary reinforcements are parallel, okay, to the axis, because this is a long side, right? So as per beam, the primary reinforcement should have been in this direction, okay. But that is not the case. Here we always take the primary reinforcement in the cross section, okay, in the perpendicular this one direction, transverse direction, and the secondary reinforcement in the longitudinal direction, okay. So you can see here also, if you cut the section AA, okay, so this section, so these bars are this line, okay. So one is the line, they have also provided bent up bars, okay, and two is the dot 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 dot, okay. So this is the this bars, okay. So this is the opposite to the beam condition, okay. Beam, this only would be the reinforcement bars, okay, and we don't provide the secondary one. Instead we just provided the stirrups, okay. So here the stirrup thing is not required, okay. That much it is not mandatory, okay. If the condition is satisfied, we don't go for stirrups because it will be unnecessary, costly, okay. And here if you see, cut the section BB like this, so here you will see the one the primary reinforcement is dot dot dot, okay, and the secondary reinforcement these lines, okay. So it will be the lines. So this is section BB, okay. So at least two bars, okay. So here should be provided in the case of bent up bars, and the distance of this bending should be 0.1 lx, okay. But lx is the end to end center to center distance, which is 3500 plus 3500 was basically the this one, the end to end distance, okay. End to end distance, basically the clear span, okay. And 250 was the width of the walls. So half of the width plus half of the width, which is the width, okay. 3500 plus 250 is 3750 mm, and zero point 0.1 lx is 375 mm, okay. So this is the value, 375 mm, okay, or you can say it to be around 1 feet, right, more than 1 feet. And thickness of slab is taken as 160 mm, which is definitely greater than 117 point something, which was required, okay. So all the conditions are satisfied. So this is the solution and the design of the slab, okay. So now if the slabs carry some kind of concentrated load in instead of UDL, distributed load, if we consider some concentrated load, then we use the effective width method, okay. So say for example, if there is a load concentrated at a distance x, okay, for a distance x, okay, so it will be transferred like this, distributed, it will go through the slab like this, in like in a parabolic way, sorry, in a trapezoidal way, okay. So this is the h, the height of the slab, this is the depth, effective depth of the slab, and this is the wearing code, right? So the concentrated load acting on a certain area, say for example this area, if the concentrated load is acting, which is a dispersed area basically, so this is the span, this is the width, okay. That is a capital B is, I think, yeah, so this is the width, then this is the effective length, and this is the effective width, okay. So like they have just represented it in a sketch, illustrative representation. So here we have to find, in order, like if there is a concentrated load, okay, so we have to find out how much is this width, okay. So they have, say for example, they have provided load here, okay, but we need to find out how much it has traversed till the bottom, okay. So this is the effective width basically, okay. So yeah, so like the a will propagate up till here, but what will be the width and the length, okay, we have to consider, okay. So that will be the effective width b, okay. So the b value is basically basically found by using this formula, okay. So this is provided in this clause 24.32.2.1 in IS 456, okay. So that according to that b is equal to kx into 1 minus x by le plus a, okay. So this a is the topmost, okay, where the area concentrated load is contact, okay, but at bottom it will be b effective width, okay. So that will be, yeah, so that will, so basically this a, I think it has been shown wrongly. So this a should be here, okay, the point of contact dispersed area. So it will this one, it will propagate here, and up till here it will reach the effective width, okay. So the width, actual width, it is acting, so effective width, okay. So that value will be kx into 1 minus x by le plus a. So this k value will be obtained from here, okay, and x is this value from the side, how much is the this one distance, L is the effective length, okay, and A is the dispersed area, the dimension of the area, dispersed area, okay. So this formula is also given in the code, okay, table 14 IS 456 2000, right. So now design of slabs, okay. So we have understood the some conditions required, prerequisites for the understanding the design, and we have also understood how to design a one way slab, okay. So we have to continue this way only. So yeah, so as we know, one way slab is ly by lx value greater than 2, okay, and ly by lx value is less than equal to 2 for two way slab, right. So if this is the condition, it is like almost a simply supported, okay, because this it is not allowing the translation, but it is allowing rotation, because it is not able to restrain completely, right. So that is the case because it is not monolithic. But if it is monolithic, okay, there is no brick wall, okay, so then it will be restrained, it will not be able to rotate, okay. And this is the 0.1 L, the extra, okay, for the bent up bars, okay. We have to provide two bars, rebars, okay. So these are supports are yielding, okay. So this support is unyielding, yeah, both are unyielding, but this is rotating, this is not rotating, okay. So yeah, so now moments in two-way slabs. So till now we have studied one-way slab. Let us briefly study what are the cases we have to consider in two-way slabs. Okay. So this is moments in two-way slabs. So simply supported on all supports. Okay. So this is Lx Ly effective length. Okay. And this is uniformly distributed load Q, which is equal to Qx plus Qy. Okay. So one is UDL on x direction, one is UDL on y direction. Okay. So so in the shorter direction, it will like this x direction, so it will be qx, right. So qx and effective length will be lx. So maximum deflection, okay, for ud, yeah, for udl in a simply supported case, okay. So it will be 5 by 384 wl to the power 4 by ei. I think this you know from mechanics, okay. So yeah, so w is qx, l will be lx, right. So the deflection will be 5 by 384 into qx lx whole to the power 4 by qx into lx to the power 4 by ei, right. And in the longer direction it will be qi similarly, and it will be ly. So the maximum deflection is 5 by 384 into qi ly to the power 4 by ei, right. So if we assume that the vertical deflection for the longer and shorter direction is same on account of no discontinuity, because there is no discontinuity in between. So then what will happen if both are equal? Okay. So 5 by 384 into qi ly to the power 4 by ei equal to 5 by 384 into qx lx to the power 4 by ei. That means qi is equal to qx into lx to the power 4 by ly to the power 4. Okay. So now as we know q equal to qx plus qi, okay, so then q will be equal to qx, just substituting in place of qi. So we will get q equal to qx into 1 plus lx to the power 4 by ly to the power 4, okay. So change dividing by this one, solving this we will get, and dividing we will get qx equal to q into ly by lx whole to the power 4 by 1 plus ly by lx whole to the power 4, okay. So mx will be equal to as we know, it will be WL square by 8 maximum moment here. So it will be QX LX square by 8. W is QX, L is LX, okay, and it will be QX LX square by 8, okay, right? So yeah, so Qx is equal to Q into Ly by Lx to the power whole 4 by 1 plus Ly by Lx whole to the power 4, right? So that is the value of Qx, and into 1 by 8 into Lx square, right? So this mx will be equal to beta x into Q Lx square, okay? So where beta x will be this one, Ly by Lx whole to the power 4 by 1 plus Ly by Lx whole to the power 4 into 1 by 8. Okay. So that will be a value of beta x into Q Lx squared. Okay. So that will be a value of mx. And similarly, Q is equal to Qx plus Qy. That means substituting again that obtained value. Okay. That formula Ly by Lx whole to the power 4 into Qy plus Qy equal to Q. So that is from the Qx side. Now let us go from the Qy side. So if Qi is this much, Qx will be Qi by Lx to the power 4 by Ly to the power 4, or Qi into Ly to the power 4 by Lx to the power 4. Yeah. So substituting and solving, we get Qi equal to Lx to the power 4 by Lx to the power 4 plus Ly to the power 4 into Q, right? So My equal to WL square by 8, Qi Ly square by 8, okay, in the longer direction, and substituting Qi value here, this one, as we obtain. So substituting this value, we get My equal to 1 by 8 into 1 by 1 plus Ly by Lx whole to the power 4 into Ly square by Lx square into Q into Lx square, okay. So yeah, so we can write this as My equal to beta y into QLX square, okay, where beta y is equal to 1 by 8 into 1 Ly by Lx whole square by 1 plus Ly by Lx whole to the power 4, right? So that is the value of beta y and into QL square, Lx square, right? So that is the value of My, and we obtain the value of Mx beforehand only, okay, Bxq Lx square. So if you see, QLX square is same for both Mx and My, only beta x and beta y value is different, okay. So even in My, we take Lx only, not Ly, okay. So Lx is constant, Q and Lx square is constant, only beta x and beta y changes for Mx and My respectively, okay. And this, yeah. So if we consider now this slab, okay, there are many panels, right? So say for example, if they have selected this panel, okay, so this panel is what, C2, right, D2, right, D3 and C3, right? So this is the name of a panel. So like this, many panels we can select, okay. So based on this panels, there are various cases, okay. So as per this one, as per IS 456, there are 9 cases that can be developed, okay. So these various panels, there can be various cases, 9 cases total, maximum, okay. And these panels are the slabs, okay. So various locations, various slabs, and if you consider these are the beams, okay. So the location of these slabs are very different at the presence and effect of various all the slabs at the various locations will be totally different, okay. So what are the 9 cases? One is interior panels, so this is an interior panel, right? Apart from that, there is one short edge continuous, one long edge continuous, discontinuous, two adjacent edges discontinuous, two short edges discontinuous, two long edges discontinuous, three edges discontinuous where one long edge continuous, three edges discontinuous, one where one short edge continuous, okay, or four edges discontinuous. So that four edges discontinuous, I think, will be where there is only one slab only, okay. So for all the four sides are exterior, okay. There is no interior, like there is only one slab, no combination, okay. So on one bay, okay, one by one bay, okay. So yeah, so that is four edges discontinuous, okay. So this total there are 9 cases, okay. So based on this, there are various this one, alpha x and alpha y value, okay. So alpha x and alpha y value are given. This is as per table 26. Okay, table 26 IS 456 2000. Okay, so there for longer span and for shorter span. Okay, Ly for different Ly by Lx value. Okay, so this is given. Yeah, so the values are given for the alpha x alpha y, and negative moment at continuous age, okay, and positive moment at mid span, okay. So all values are given, okay. So basically the moment coefficient is given, So these coefficients, moment, negative moment and positive moment, we have to just add with our W into L. So W into Lx is capital W and L L. That's so this value is constant. So these values we have to change accordingly. Okay. So as per this. Okay. So yeah. So that is for the interior panel. So similarly for other cases also, it is given in table 26. Okay. Please refer that. So yeah, so with this we come to the end of today's lecture part. Now let's go to the solved problems. Okay. So first problem is unit weight of concrete is 25 kilonewton per meter cube. Self weight of slab with overall thickness of 120 will be equal to how much? 3, 1.5, 13.5, or 25. So unit weight is, if unit weight is 25. Okay. So self weight will be 25 into overall thickness, which will be 25 into 0.12, right? So 25 into 0.12 will come 3. So 3 kilonewton meter square will be the self weight of slab. Okay. So A will be the correct option. Okay. So as you can see, A is the correct option. Second question, overall depth of the beam is obtained by adding effective depth and clear cover, minimum cover, effective cover, nominal cover. So we all know effective depth plus the this one effective cover. Okay, so that will give you the overall depth, that is small d plus 5 by 2 plus clear cover or nominal cover. Okay, so 5 by 2 plus clear cover or nominal cover is effective cover. So effective cover is the correct answer. C is the correct option. So as you can see, C is the correct option. Third question, according to IS 456-2000, which of the following is false in regard to the minimum reinforcement in slab? Okay. A, the mild steel reinforcement is either direction, in either direction of slab shall not be less than 0.15% of the total cross-sectional area. B, the high yield strength deformed reinforcement in either direction of slab shall not be less than 0.12% of the total cross-sectional area. C, both A and B. D, neither A nor B. So which will be the correct option? So yeah, so both the options are true. Okay, if it is we just discussed I think few slides back. If it is HYSD bar, so minimum reinforcement for slab will be 0.12 B into capital D. Total cross sectional area is B into capital D. So that is for HYSD. And for mild steel, the reinforcement requirement minimum will be in case of slab will be 0.15 B into capital D. Okay, percent. So both are correct. So neither of them is wrong. So false. Okay. So so false is so this option is false basically. Neither A nor B. Okay. So which of the following is false? Okay. So both are correct. Okay. So no one is wrong. Okay. So neither A is wrong, neither B is wrong. Okay. So nor A is false, nor B is false. Okay. So both are correct. So D is the correct option. Neither A nor B is false. Okay. Because both are correct. So D is the correct option. So you can refer this clause. Okay. As per IS 456. So as you can see, D, neither A nor B is the correct option because both are correct. Neither is false. Fourth question. Consider the following statements. One, horizontal distance between parallel main reinforcement bars shall not be more than 3 times the effective depth of solid slab or 300 whichever is less. Two, the horizontal distance between parallel reinforcement bars provided against shrinkage and temperature shall not be more than 5 times the effective depth of solid slab or 300 whichever is less. The maximum diameter of reinforcing bar shall not exceed 1/8 of total thickness of slab, and the nominal cover should not be less than 20 Okay, so 4 is correct. Nominal cover should not be less than 20 unless it is mild steel and maximum diameter is less than equal to 12. So it should always be 20 other than less than equal to 12 by dia bars and nominal mild exposure. Okay, so 4 is correct. Okay, it should generally be 20 Maximum diameter reinforcing bar shall not be 1/8 of total thickness of slab. So I think this is also correct. Okay, so it should not exceed. Okay, this option is this condition is also correct. Okay, shall not be more than 3 times the effective depth or 300 This is also correct. Only I think this is wrong because against shrinkage and temperature it should not be more than 5 times. Okay, the effective depth of slab or 450 Okay, this is not 300. 300 is for this. Okay, horizontal for the normal case. It should be not more than 450. So second option is wrong. Okay, so B will be the correct option. So as you can see, horizontal distance between parallel reinforcement Okay. Bars provided against shrinkage and temperature shall not be more than 5 times the effective depth of solid slab or 450 mm, whichever is less. So, as you can see, B is the correct option. Okay. Then, fifth question, match list 1 to list 2. Okay. To the basic values of span to effective depth ratios of one way slabs for spans up to 10 meter adhering to the vertical deflection limits. So basically, simply supported will be 20. Okay. So A will be 2. So this option. Okay. Then cantilever will be 7. Okay. We discussed. B will be 1, as you can see. And continuous will be 26. Okay. So C will be 3. Okay. So yeah. So C option only. A2, B1, C3. Okay. So C is the correct option. So you can refer this lecture also. So as you can see, C is the correct option. Okay. Sixth question. So these are the conditions, okay, and of a simply supported roof slab. Okay, these are the parameters given. So we have to consider see the following statements. So assuming a modification factor of 1.25, the overall depth of the slab is 165 mm. The slab is subjected to a factored shear of 25 kilonewton. The slab is under reinforced. The spacing of mean reinforcements shall not be more than 300 mm. The section is safe against shear and deflection. We have to see. Okay. So Ly by Lx is 7.5 by 3.5, which is greater than 2, therefore one way slab. Modify we have assumed to be 1.25. Oh, sorry. In the first condition only statement is given, assuming 1.25. So span by D will be, because it is simply supported, right? Yeah, so it will be 20 to 1.25, which is 25. So D will be 140 mm, right? So overall depth will be 140 plus 20 plus 5, which is 165 millimeter. Because I think clear cover is 20 mm, yeah, and 10 mm part. So yeah, 10 by 2 is 5. Yeah. So 165 mm. So therefore, statement 1 is correct. Okay. Next, if you see effective span will be list of center to center distance and a clear span plus effective depth. So that will be 3.64 meter. Okay. So design loads. Okay. So self weight will be 4.125 kilonewton per meter. Imposed load 4. Okay. And floor finish 1. So total load will be 9.125 kilonewton per meter. Okay. So factor design load WU will be 1.5 times 9.125, which is 13.69 kilonewton per meter. So factored moment is WU L square by 8, which is 22.67 kilonewton meter, and factored shear is WL by 2, which is 25 kilonewton. So yeah, so so factored shear condition is correct. So 2 is correct. Then effective depth required from we will consider from the concrete side. So generally we always consider from concrete side, okay, unless we require area of steel, okay, because we are mainly basically dealing with concrete. Okay, steel we are like we are mainly trying to design it less as compared to concrete to make it under reinforced. Okay, so we are not mainly considered about bothered about steel. Okay, we are mainly considered of concrete. That's why it is RCC design. Okay, not steel design. So yeah, so we will always mainly go for concrete from all aspects. Okay, unless we require the area of steel. Okay, so that's why mu limit is 0.36 into FCK into XU max by D into 1 minus 0.42 XU max by D into BD, right? So for limiting condition is 0.13 FCK BD square. So D required will be how much? 90.6 mm, and we have provided 140 mm, right? So it is safe, and because it is more, so it will be under reinforced. Okay, because so we will design in such a always we will go for design in such a way that steel fails first. Okay, so we are not that much bothered about steel. We are mainly bothered about concrete. So statement 3 is also correct. Okay, but if say for example the situation would have been such that we were bound to provide some we were bound to provide the D provided less than 90.6 because of some reason, which will never happen. But say for example if we hypothetically had to provide 90 or 85 millimeter, then we have to definitely make the structure over reinforced so that although concrete fails, the steel is able to hold it. Okay, but that is never this one. That is never accepted. Okay, never desired. Okay, it is always desired to be under reinforced. So this is the statement 3. That is slab is under reinforcement. Okay, reinforced. So it is correct. Okay. Then yeah, so as I told you, for only finding the area of steel, we use the steel moment carrying capacity. Okay, so we have put these values. Okay, mu value is this much and other values. So we get area of steel is 483 mm square. and we are providing 10 bars. Okay, so 1 10 bar is 78.5 square area. So yeah, so spacing of bars will be 1000 by 483 by 78.5, which is 162.5 So the spacing should be minimum of 162.5 uh, 3D, that is 3 into 140, 420 and 300 That means 162.5 Okay, so whichever is less. So we have to rounding off to 10, nearest 10. We have to provide hence 10 bars at 160 center to center, which here is wrong, because here it is written shall not be more than 300 but it should be shall not be more than 162.5 or 160. Okay, so 4 is incorrect. And checking for shear, tau v is 0.18 megapascal, and using pt and the chart. Okay, sorry, yeah, from the table, from the table is 456 table 19, table 19 using table 19 m20 and pt, right? Yeah, M20. So using PT, M20 and table 19, we get tau C value as zero point 0.4. So as 0.345 is less than zero point 0.4, it is safe against shear. We don't have to provide in slabs stirrups. Okay. So the check for deflection. So yeah, we have to provide. That is an important thing for slab. So required AST was 483 square. Yeah, provided AST will be 490 square. Okay. So from this figure, FS value is 237. Therefore, modification factor will be 1.55. Therefore, L by D max value will be 20 into 1.55, which is 31. Okay, and L by D provided is 26. So as 26 is less than 31, so it is safe against deflection. So 5 is correct. Okay, only 4 is incorrect. So only 4, that is D. Okay, so D is the, so which is incorrect 4. So D is the correct option. So as you can see here. Seventh question: the cantilever panel of a one-way slab is subjected to uniformly distributed imposed loads of 5 kN per meter square using M20 Fe415. The load of floor finish is 0.8 kN per meter square. Overhang is 1.8 meter. Width of support is 300 Consider main reinforcement bar diameter is 8 Assuming the following statement, consider the following statement. Assuming an initial modification factor of 1.5, the overall depth of the slab may be taken as 200 rounded to the nearest multiple of 10. The effective span is clear span plus 1 by 3 of the effective depth. The minimum area of steel shall not be less than 480.31 square. The spacing of main reinforcements shall not be more than 105 So which of the following are incorrect? Okay. So yeah, so if you see, yeah, modification factor is 1.5, right? Span by d will be, because it is cantilever, it will be 7. Okay, 7 into 1.5, 10.5. We have assumed clear cover is 20 because it is the minimum, right? So d is equal to 1800 by 10.5, which is 171.42 Okay, so overall depth will be 171.42 plus 20 plus 4, which is 195.42 or 200. Okay, rounding off. So therefore effective depth will be this one 200 minus 20 minus 4, which is 176 or 175 so d provided should be 175 which is this one, which is right, and overall depth is 200 that is also right, so one is correct. So second question: effective span of a cantilever shall be taken as its length to the face of the support plus half the effective depth. Okay, so effective span of for cantilever is length to the face of the support plus half that effective depth, because one end is free, right? So it is one half, not 1 by 3. So statement 2 is wrong. Okay. Third statement. So for third statement, let us see. Design loads is self weight of slab 5 kilonewton per meter, imposed load 5, floor finish 0.8. Okay. So total load will be 10.8. Factored design load will be 1.5 into 10.8, which is 16.2, right? So factored moment will be 28.62. Okay. Factored kilonewton meter. Factored shear is 30.45 kilonewton. So effective depth required will be D 101.8 millimeter. Okay. So we have provided 176 or 5. So 175 is more than 101. So it is safe and under reinforced. So area of tensile reinforcement will be 480.31 square using the this one formula. So yeah, so it is correct. 3 is correct, and 4 is let us providing 8 bars in tension side. So area is 50.27. So spacing will be 1000 divided by 480.31 by 50.27, right? So that will be equal to 105 Okay, so spacing should be minimum of 105, 3 into 175 and 300, which is 105 itself. So yeah, so 4 is also correct. So only 2 is wrong. Okay, So hence provide 8 bars at the area, 100 center to center. So A is the correct option. Okay. So eighth question: a reinforced concrete slab for a hall measuring 8 meter by 16 meter is supported on RCC beams 250 wide. The beams are spaced 4 meters center to center. The imposed load is 4 kilonewton per meter square. The bearing of the beams is 200 millimeter. Consider M20 grade of concrete and 10 diameter. Fe415 bars and an effective depth of 125 Clear cover of 20 What is the effective span of the slab? Rounded to 3 decimal places. A 3.95 meter, B 4 meter, C 3.550 meter, D none. So overall depth is 125 plus this one 20 plus 10 by 2, which is 150 effective span is you're referring to clause 22.2.b IS 456. So effective span will be width of support or bearing, which is 200 so clear span will be how much? 4000. Yeah, so clearing yeah, so center to center is 4 meter, right? So it will be effect clear span will be 4 meter minus 0.25, right? So 4 minus 200 yeah. So yeah, sorry, so bearing of the beams is 200 right? So it will be 4 minus 0.2. Okay, so 4000 minus 200, which is 3800 okay. So after that, because we are considering about the connection, okay, so not the beam, okay, because we are considering the slab, okay. So the bearing is 200 not 250. So clear span is 4000 minus 200, that is 3800 So 1 by 12 of clear span is 316.5 and width of support, okay. So width of support is this one 200 which is less than 316.5 okay. So we can design it as per the effective span will be as per the as per the this one RCC, as per the simply supported simply supported case, which is nothing but the clear span plus the effective depth, okay. So clear span plus effective depth is generally taken. So yeah, so uh, it will be this one 3.8, okay, 3.8 plus 0.125, okay. So 0.125 is the, yeah, so it is the effective depth. So 3.8 plus 0.125, which is equal to 3.925 meter, okay. So that, or 4 meter, 4 meter is the center to center distance, okay. So that is already provided, and this, so we always need to take the minimum. So minimum of 3.925 or 4, which is 3.925 itself. So yeah, so A is the correct option. Okay, so what is the space is effective span of the slab? It is 3.925 meter. Okay, rounded to 3 decimal places. Ninth question: a reinforced concrete slab for a hall measuring 8 meter by 6 meter is supported on RCC beams 250 wide. The beams are spaced 4 meters center to center. The imposed load is 4 kilonewton per meter square. The bearing of the beams is 200 Consider M20 grade of concrete and 10 dia, Fe415 bars and an effective depth of 125 clear cover of 20 millimeter. So consider the following statements abiding by 12 with 12 table 12 and table 13 of IS 456 2000. So these are the moment and shear coefficient tables. Okay. So maximum negative moment occurs at support next to end support. Maximum positive moment occurs at the midspan of the interior spans. Maximum shear force occurs at outer side of the support next to end support, or the section is under reinforced. Which of the following statements is or are correct? Okay. So yeah. So as per the last question, the overall load is 150 effective span is 3.925 load calculation, self weight is 3.75 kilonewton per meter, floor finish is 1 kilonewton per meter, total dead load is 4.75 kilonewton per meter, factor dead load is 7.125 kilonewton per meter. So imposed load is 4 kilonewton per meter. I think, yeah, it is mentioned, and taking unit weight, and factored imposed load will be 6 kilonewton per meter, and we assume load of floor finishes 1 kilonewton per meter square. Okay, so the beams are spaced this one 4 meters center to center. Yeah, so hence number of spans will be 4 because it is 16, right? So yeah, so we have to take the maximum. So yeah, hence number of spans will be 4. So here, this for these conditions, always the spans should be more than 3, right? So we can take this condition, we have to take 6 millimeter. There we'll get 4, otherwise other 8 meter we'll get only 2. Okay, so hence number of spans is 4 with 2 interior spans and 2 end spans, 2 supports next to end supports, and 1 interior support, right? So as per 12 table 12 and table 13, so these are the coefficients. Okay, so if we consider for moment coefficient, both moment and shear coefficient, if we consider DL plus LL, okay, fixed. This is alpha value, okay. Alpha DL plus LL fixed, which is the moment coefficient. We get 0 plus 1 by 12 minus 1 by 10 plus 1 by 16. These are the values, okay. And for shear coefficient beta, okay, which is beta, but DL plus LL fixed, we can get this condition, okay. So this is for DL plus LL fixed for moment as well as shear coefficients. In the case of LL not fixed, okay, without DL, no DL and LL not fixed, these are the moment coefficients and these are the shear coefficients, okay. So these are the different cases, okay. So for LL not fixed and no dead load, these are the values, and for DL and LL fixed, these are the values, okay. So adding both, okay, adding both the coefficients, we get like this, okay. So we get these are the coefficient total, okay. So assuming n supports are this one simply supported, okay. So assuming n supports are simply supported, that's why it is 0, okay. Otherwise we would have, we need to take these values also. So yeah, so apart from this, these values are obtained from the table itself, okay. So from this only we can predict everything, okay. So from this we can say maximum negative moment occurs at support next to n support. So maximum negative moment, yeah, occurs at support next to end support. So yeah, so statement one is correct. Okay, one is correct. Okay, so maximum positive moment occurs at the midspan of the interior span. So maximum positive span moment occurs at midspan of interior. No, so this is wrong because maximum moment occurs here. So this is at end span. Okay, so middle of end span, okay. So middle of this one, yeah, middle of end span, the maximum positive moment occurs, okay. So 2 is wrong, okay. So 2 is wrong. And then this one, maximum shear force occur at outer side of the support next to end support. So yeah, so maximum shear force occurs at support next to outer side of support next to end support. So this is correct, okay. So maximum shear force occurs at outer side of the support next to end support. Now 3 is correct, okay. And 4, okay. So 4 we have to find out the value. So 2 is incorrect, 1 and 3 are correct, okay. So from this only you can say I think B will be the correct option, but okay, let us see. So for this, under whether it is reinforced so effect or not, under reinforced or not. So effective depth is 87.74 mm, which is less than 125 mm. So required is less than provided, okay. So provided is more, so okay. So mu limit is 43.125 kilonewton meter, which is greater than mu, okay. So therefore we can go for under reinforcement. So the section is under reinforcement. So 4 is also correct as we just predicted. So yeah, so B is the correct option, okay. So as you can see, B is the correct option, okay. So yeah, so last question. Yeah, a reinforced concrete slab for a hall measuring. So same problem, I think, the same question maybe. I think, yeah. So the required area of steel, okay, shall not be less than 440 mm square to resist the maximum positive moment in the slab. The required area of steel shall not be less than 515 mm square to resist the maximum negative moment. The slab is safe in shear. The spacing of the distribution reinforcements shall not be more than 270 mm center to center if rounded to nearest multiple of 10. Okay, so which of the following are correct? Is or are correct? So yeah, maximum negative moment is 21.25 kilonewton meter. So area of steel will be 515 mm square. Okay, and spacing will be 152 mm for 10 mm bars. So yeah, so less than 150, yeah, so less than 152, 3 into 125 and 300, so definitely 152, okay. So we can provide 10 mm bars at the rate 150 mm center to center. So 2 is correct, okay. So yeah, 2 is correct, okay. 515, positive moment 18.39 kilonewton meter, okay. So yeah, maximum will always be negative because hogging, okay, because then only it will be able to, slab will be able to take the loads. If this is more than this, then the slab will damage, okay, because hogging, like hogging is resisting, okay, so it will not be able to resist, okay? So it should always be high, it should be less, okay? So here in this case AST value will be 440 mm square, so spacing is 178, so we can provide 170 mm, 10 mm bars, 170 mm center to center support, okay, at the supports on the tension side. So yeah, we can provide the spacing as 170 mm, okay. So yeah, so it's 440 mm square and 170 mm center to center spacing, okay. So 440 mm square. So 1 is also correct, 2 is also correct. Checking for shear, tau v is 0.24, and tau is C is 0.44. So tau is less than tau C, so it is also safe against shear. Okay, so 3 is also correct. Okay, and yeah, and fourth question is distribution still. Okay, so that is a secondary. Okay, so we provide the minimum, which is 0.12% for HYSD because it is 415, right? Yeah, so it will be 0.12 B into T percent, so which is 180 mm squared. Okay, so yeah, so we can provide 8 mm bar at 270 mm center to center. So yeah, so calculating we get 270 mm. Okay, center to center to near rounded to nearest multiple of 10, and rebar size is 8 mm. Okay, definitely it will be less than the primary reinforcements. Okay, so all the statements are correct. Okay, so each of the statements are correct. Okay, so these is the correct option all. Okay, so yeah, so with this we come to the end of today's discussion. Okay, so let us again meet next Sunday evening, and yeah, and I hope that you have a good good week coming. Okay, coming week, so best of luck. Okay, so with this I would like to end today's discussion. Thank you.